Okay, so Johnny will give the second of his talks. Thank you very much.
Well, I don't know whether you all were at the previous one. So, all I said the other time was in some sense on preparation, and now I want to discuss what you can get out of this approach, at least what has been obtained so far. Essentially, let me recall some, which were the principles of an approach. The basic fact was that large deviation rates were good thermodynamic functionals to use also out of equilibrium. And I quoted Einstein, who was the first to show, to have a large deviation estimate in which the rate was the entropy, or the free energy is the same. And actually what comes in the exponent is what I call the minimal work to create a fluctuation. The second point was, I mean, in out of equilibrium you cannot avoid dynamics, and so and you have also to restrict the class of systems, and the restriction is to diffusions, which are, I mean, what is perhaps the most ubiquitous phenomenon in nature, and and so you have to assume some macroscopic evolution equations. These were provided by conservation laws, which can be, for example, matter, electric charge, or and so on. And then you need some, in order to get a closed equation, you must have what are called the constitutive equations. So equations which express the current, because what characterizes a system out of equilibrium typically is a flow. There is a current flowing through the system. And that is the novelty. And as we shall see, the current will be treated as a thermodynamic variable, and it has some peculiarities because time is involved in its definition. So what are called constitutive equations is the expression of the typical current, of the dynamic current in terms of thermodynamic variables at the same instant of time. That is important. Otherwise, there would be retardation effects and so on. But we assume that on the scale, macroscopic scale, that is the correct situation. So these are these equations. So there are, and then you have a boundary term where the condition of being equilibrium or non-equilibrium appears. It appears through the boundary conditions. If the boundary conditions are the same, even if the system is in contact with the reservoir, I mean, it is in an equilibrium state. But if the boundary conditions are different, then this produces a current through the system. And the current could be also quite large, but it is somehow, there is the hypothesis of local equilibrium, which allows you to define the variables, which are averages of microscopic quantities over macroscopic volumes. And what is characteristic of this is these two coefficients, which are called transport coefficients. One is the diffusion, and the other one is the conductivity or mobility, which expresses the reaction of the system to a weak external field. So this is all these are physical hypotheses, And of course, they have to be verified by the consequences. Of course, I mean, there are mathematical models behind this, and typical models that have been studied in the last decades are lattice gases. So the next step is how do we introduce fluctuations? We introduce fluctuations by adding to the current a term which is proportional to space and time white noise. Okay, why this choice? I mean, the idea is that the system at the macroscopic level is still immersed in a I mean, the macroscopic variables, they are still perturbed by some, for example, thermal fluctuations, which can be considered as a kind of external field. So the simplest thing is to add the perturbation to the current, and again, this is a physical principle. It has to be verified by the consequence. In the linear case, when the hydrodynamics is linear, this was introduced by Landau long ago. But the interesting thing is that, I mean, all the interesting phenomena are connected with non-linearity. I pointed out that the perturbed hydrodynamic equations, we don't know yet how to give a mathematical meaning to this, but as I emphasized the other time, in reality we are using essentially only this, which you see, if you bring the hydrodynamic current on the other side, then you can express, this is a Gaussian process, so the difference between the fluctuation with respect to the hydrodynamic behavior will have a Gaussian distribution. Well, actually, it's more complicated because the continuity equation has always to be satisfied. So, okay, then from the previous equation we had inferred that a plausible lag deviation estimates, if you are at constant temperature, but you may have other gradients, for example, electric gradients, and so on, is given by this formula, which is a quadratic, which has a simple interpretation because it is the dissipation of the extra current during a certain interval of time and overall space. And again, there are many physical assumptions in all this approach, but the models have been a very important guide in the same sense as the Ising model has been an important guide, for example, to understand critical phenomena. The Ising model is oversimplified, but at the macroscopic level essentially gives the correct answer because they don't depend on the details. And the hope is that something like this happens also in this dynamical situation. So the point is to generalize this formula even when you have gradients of temperature, and I indicated that the minimal work. So first of all, instead of the Boltzmann constant, more generally you may have this epsilon is a scaling factor between the microscopic and the macroscopic situation, and So that term essentially tells you how many degrees of freedom you have. And, typically, in the case of lattice gases, this is the number of sides of the system in all of the now this work that to create a fluctuation is made of two terms. You have the system in your stationary state, so there may be a fluctuation in the initial condition, and then there will be a time trajectory. So this will be actually the analog of the entropy in the equilibrium case, and this will represent the dynamical part, which is given by the formula that I recalled previously, and then we obtain the equations to calculate this quantity here. And now let's see what is the situation. Actually, the line deviation function associated to the invariant measure is related to this dynamical part by essentially, you calculate the work that is necessary to go from the stationary state to the fluctuation. And so it is the inf over all possible trajectories of this dynamical part. And if you want to, because our basic formula contains both current and thermodynamic variables, which are the rho. Now you can get something, a lag deviation functional for the density, also for the thermodynamic variables, by essentially generalize the Kramer argument to this setting. I think the first paper in that direction was done by Varadan, Kipling-Sol and Varadan, in a very difficult paper. Then it has been, to a certain extent, simplified. So you introduce an extra external field in such a way that the fluctuation becomes the typical value. And then you compute. You see that you need only a gradient type field, which is obtained by solving this elliptic equation. So this is, because this is given, you assign the trajectory, which is the fluctuation, and so this rho is assigned, and then this is a second order equation for H. Okay, this is the end, the result. This K is the, what I call the Onsager matrix, is the mobility or conductivity, but with these gradient pairs, which are, this is an elliptic operator, to take into account that you allow space dishomogeneities. But what is somehow intriguing, that in this way you get exactly what you would get by applying the finite dimensional Benson-Friedin theory to this case. So everything goes as if this this equation here were perfectly meaningful, and so I would expect that the day we are able to make a theory of this, the lag deviation function is in fact given by that expression. So clearly there is some mathematics to understand. Okay. Well, there are the Hamiltonian structure, and we consider this functional here like a Lagrangian, and then there is an associated Hamiltonian, And the Hamiltonian equations are just the Euler equation associated to the variational principle. This I skip. Then we discuss time reversal. Time reversal as, and I emphasize what I mean by time reversal. So these are again physical assumptions. There is a dynamics which allows you to have the trajectory going backward. So as a physical example, I discussed the heat naturally goes from high temperature to low temperature, but if you are able to spend some work, you can have heat going from lower temperature to a higher temperature. So it's a natural physical assumption, and this defines the time reversal deviation function. And the next assumption is that this time reversal dynamics admits a hydrodynamic description. So the structure of this, let's call this adjoint hydrodynamics is has the same structure as the other one, and from this you get several consequences. So, okay, the adjoint has the same structure, but with a different expression for the constitutive equations. A different expression which may be non-local. So far we, this can, actually it will be non-local in general, non-local in space. We shall see why in a moment. So from this discussion of time reversal, you get these symmetric equations in the current and the adjoint current, relating it to this gradient of this functional derivative that I call the thermodynamic force. And then it's convenient to split the current into a dissipative part and which is symmetric under time reversal, and a part which is antisymmetric under time reversal, by defining this symmetric part in this way. So it's related, essentially, is the thermodynamic force with mobility in front. Okay, and then doing this, you discover that these two types of currents are in fact orthogonal. Orthogonal when you integrate over x, and the metric is given by this mobility, which in general will be a nonlinear function. And if you express now, you go back to the equation, just to the definitions, then you discover that this orthogonality relationship can be written in this way, which is an equation for this non-equilibrium free energy. And then you discover that this is nothing but the Hamilton-Jacobi equation of the variational principle. So that is the structure. And then, I mean, in terms of these two currents, it's easy to write. This is the original hydrodynamic equation, and this is the adjoint hydrodynamics. There is this term which changes sign, and I've shown to you that it behaves like there is nothing electric, specifically electric in this argument, but it behaves like a Lorentz force, essentially, which may have an interesting interpretation as a kind of duality principle between external fields and boundary conditions, which is the dual of the whole effect. Okay, then you can identify the optimal trajectory, which is related to the joint hydrodynamics, and then I mean this was an logical experiment done 20 years ago here in England. So this I don't want to discuss now, but I will just one word to say what it means. Like for symmetries, you have a passive interpretation and an active interpretation. For example, for parity, you may just make a reflection in the environment or in the system. And so here you can take a similar attitude with respect to fluctuations. You can just wait for the age of the universe until your fluctuation is produced, because these are the times involved. Otherwise, you may create it with a minimal cost, and the problems are entirely equivalent. Okay, and this will be important because we gave a more realistic. So this is the formal aspect. All of this I want to skip. But now, can you use this Hamilton-Jacobi equation to make real calculations? Well, for the models which have been essentially solved mathematically, like a simple exclusion, zero range, or the Kipling's-Marquardt or Pessutti model, you can solve it. I will show you how you solve it in this case of the simple exclusion process. And actually this was very important for us. Then I will discuss, I will tell you who are the group in Rome. Because this V functional was calculated for the first time by Derrida, Leibowitz, and Spohn by solving by brute force the microscopic model. And then they calculated the large deviation function. So it was a 40 pages calculation. And then we decided that, I mean, if in some way we should be able to solve the Hamilton-Jacobi equation in the same situation. And actually from the Hamilton-Jacobi equation it follows in 3 lines. So this showed that we were more or less on the right track. So what you solve it by isolating the equilibrium part in this derivative, and this is the unknown part. Then you do some purely formal manipulation. You insert it into the Hamilton-Jacobi equation, you add and subtract something, and you end up with this expression, which you see is a kind of scalar product between these 2 expressions. Now, one way of making this vanish is either factor may vanish. Now, if you make this vanish, you get a trivial solution. But then you may have this vanishing, and actually this gives you the right solution. The right solution is defined by additional conditions that I don't discuss, which are mathematical. It has to be the maximal solution of the Hamilton-Jacobi equation. So, and which is also obeys also an H theorem in statistical mechanics and so on. So you have to solve this equation, which is a nasty-looking ordinary differential equation, but I mean it's just in one variable, and then you have that the final expression for this out of equilibrium functional is this is the equilibrium part, and then you have this, and this is clearly non-local because you see when you solve this equation, this phi will be a non-local functional of this inhomogeneous part. That has raised a lot of discussion because this, as we shall see, produces long-range correlations which have been measured. And people have speculated whether these are similar to what you get in critical points. But I think that the question is still not completely clear. The situation is entirely different from the critical point. But, okay, so you see, you get the important thing I want to emphasize that you get a non-local expression. So you must expect that calculations that when you take you see, this is the Legendre transform of this function, like in equilibrium, is the generating function of the correlation function. So you must expect that long-range correlation exists and we shall see that they are strongly connected with the non-linearity. So let's speak a little bit about correlation functions. So you make a Legendre transform and you write the Hamilton-Jacobi for the Legendre transform of this non-equilibrium free energy. You get this expression, and then you expand, and and you get a set of a couple of equations, but these are horrible. But if we discuss the two-point correlation, this can be discussed in detail. Then you see the following, that well, there is the equilibrium part, which is the macroscopic level is just a delta function, because if there are no long-range correlation, when you scale going to the macroscopic level, you get a delta function. But then there is another part, which is given by this inhomogeneous equation, where this is an elliptic operator, and and which is given by contains the usual coefficients. So the diffusion coefficient and the mobility. So now the interesting part is to see this inhomogeneous part, because you get the long-range correlation only if this part is different from zero. Otherwise, you don't get anything new. Now, this term alpha, you see, contains the divergence of this expression here. Now, the divergence of this term here, which is the stationary current, is zero. Because you cannot have accumulation or empty your system. So this part doesn't contribute to this divergence. Then if this product were linear, then at this point you will get zero again. So this fact being, typically, for example, for the simple exclusion, this d is equal to 1. So it's the identity matrix. So here you get the derivative of the mobility, which is a quadratic function. So you see immediately that if it were linear, then this term would give zero. You need at least you need some dependence of the mobility on the density, which is more than linear. Otherwise, you don't get. But if this term is different from zero, then you get long-range correlation. Now, to understand what happens, in a paper of a long time ago that I did with one of my students, we examined the case whether you can get long-range correlation also in equilibrium. And then we discussed the Galver plus Kawasaki dynamics, which is the simplest, which is like the the stochastic quantization of the on the scalar field, essentially. But I mean, here we are at long range. We don't have renormalization problems. And to see, and then we discovered the following, that if you have a small violation of time reversal that involve, that do not show up, because when you go from the microscopic to the thermodynamic level, you lose information. So if you have what I call a small violation of time reversal of detailed balance, it do not show up at the macroscopic level, you don't get any long-range correlation. I'm speaking of equilibrium. But if your violation of time reversal shows up at the macroscopic level, then you get immediately long-range correlation. So the deep reason for this range correlation seems to be connected with the violation of time reversal. But I mean, the question is open. Okay. Now this is an example of a real experiment. I mean, this was done by essentially Sengers, was the leader. And you see, it doesn't matter to understand what are these amplitudes, but let's only say that if there are no long-range correlation, these are this would be some flat lines. So be a constant. But this indicates the deviation, and the presence of this line indicates that you have long-range correlation. You essentially take the logarithm of the correlation function. This as we have power law behavior, scaling power behavior, and so these are essentially the exponent. The graph of the log of the correlation function.
One sec. May I ask what's like the experimental setup that was in there?
The experiment, what was
How?
This was done by a container with different temperatures. And you see, here you have in fact the gradient of the temperature squared. And we're done with this, organic liquids like hexane, I don't know the formula. But this is a real experiment, and many experiments have been done in this way. These were done about beginning of the 90s. This is I know this is Journal of Physics, that's a matter, but there is okay, now let's go for one of the main novelty of this approach, which is do the thermodynamics of currents. In the same way as you do thermodynamic, in equilibrium you may think of your thermodynamic variables also as space averages. And here the natural thing is to consider time averages. The current involves time in its definition. So you define a time average of this current, And you are interested in the fluctuation of these quantities when the time becomes very large. So our formula, basic formula, allows us to calculate what is the associated thermodynamic functional, which will be also the lag deviation functional. So we define this quantity. So you take the minimum of our usual quantity, which is this one, the usual quadratic expression. And so we take first the infimum over all possible currents, and then we divide by the time, and then we take the limit as t goes to infinity. And this had never been introduced before, and the probability of observing a fluctuation in this time average current is given by this. So this is the lag deviation function. Okay.
What is epsilon in all of this?
Epsilon is this usual scaling parameter between macroscopic and microscopic. I mean, at constant temperature is the Boltzmann constant, which is a very small number, in fact. Okay, now the point is that as in equilibrium, you must ask whether there are singularities in these functionals. I've introduced two functionals: the analog of the free energy out of equilibrium, which is this V that we calculated for the simple exclusion, and now this new functional which describes the fluctuations of the current. Okay, so now the interesting fact is that to this functional associated new phase transitions, which most of them can take place only out of equilibrium. Some of them can take place also in equilibrium. Okay, now this problem of current fluctuation was discussed first by Bodino and Derrida, but they introduced an assumption which in fact was a limitation of their approach. They assumed that these current lag deviations were supported by constant by thermodynamic variables which were independent of time. So the rho should be independent of time. This means that these currents must be divergence free, because in order that by the continuity equation, if the rho is constant, then it's the time derivative is zero, and then this implies that the current must be divergence free. So, in our language, what they did, they assumed that the functional to minimize is essentially this one. So that this J is a function of rho, and you have to take. However, it's clear that in general, this phi functional that I introduced before, this one, you take an inf over a much larger set of trajectories, because here you include even j's which are not divergence free. While what they did essentially was the same variational principle, but restricting the minimum so to divergence-free trajectories. So in general, you have this inequality. This phi is less or equal than this. And now, now let's talk about the phase transition. It may happen that, I mean, in the case where they applied it, which was the simple exclusion and zero range processes, what they were doing was entirely correct. But the point is that their additivity principle doesn't apply always. Now, however, still within this scheme, so within the additivity principle, you may have more than one solution to this minimization problem. And in fact, many, for a wide class of systems, these cases in which you have, may have several phase transitions has been discovered by these people, by Caffrey, who are at the Technion in Israel, and Leconte, who is a well-known French physicist. And they have discovered that you may have a wide class in which you have this phenomenon. And but then let's consider the case in which this phi, so for small current fluctuation, fluctuation of this average, this phi has this very simple quadratic form. However, think of a situation in which, for example, we have ring geometry, and you have a fluid in this ring. Then, and you consider fluctuations, even at equilibrium, then for small fluctuation, your system, your density will be constant and remain constant in the fluctuation. But there will be a critical current for which the system prefers to go into a state of time dependence, and then you have a traveling wave. So you have a periodic case. We called this time crystals long ago. Now time crystals are somehow fashionable, but in a different context, in quantum mechanics. Now, however, this time it may be useful. This now in simulations, this phase transition has been seen by these people have done were very capable in doing simulations, and then you see that you don't have. Let's say this is the density, if you want, and this is the space, and this is the intensity of the fluctuation. And then you see that for small fluctuation, you get a flat profile. But starting from some point, you start getting a peak, and this the peak will be the peak which will constitute the traveling wave. Heuristically, they have been found by Derrida and Bodinot in the case of the simple exclusion. And they also, they found that this, and we studied at the same time another model, which is the same for which for which this simulation has been done, which is this Kipnis-Mercure model of weak conduction. But in our case, we were able to do it essentially rigorously. We proved analytically the existence of this traveling wave solution.
So, are we still in the ring geometry? Is there a temperature difference across the ring this way?
No.
What drives the
You are
current?
in equilibrium.
We're in equilibrium.
Yeah, real equilibrium. And then you have a fluctuation in the current. Now, The fluctuation initially is supported by there is no change in the profile of the density, remains constant. But when the fluctuation becomes large, then the system prefers a traveling wave. Seeing from the other side, from the control point of view, suppose you want to create the fluctuation but with the minimal work, dissipating as least as you can. Then for small fluctuation, I mean, you will have you introduce an external field, so to do that. For small fluctuation, a constant field, it's enough, and the density remains constant. At some point, you will have to introduce a time-dependent external field, which supports the traveling wave. So you see, it may be interesting also from the point of view of saving energy, this, because in this other interpretation. Because the fluctuation, I mean, the fluctuation is the passive point of view, you just wait.
But the external field sounds to me like it's just changing the activity or something like that in order to make the density, before we get this traveling wave. In order to
Well, I
get
mean,
the density.
you get an explicit expression from the Bellman equation of the
Yeah, I understand. I'm just trying to understand the setup which would actually create.
I mean, how easy it is, I don't know. But you see, I mean, if you suppose you are able to solve the variational principle, then you find a row which is time dependent, and the external field that you have, and then you have to find this traveling wave. And then the external field that you have to apply is just directly connected with this traveling wave.
But that has to be time dependent too.
Yeah, that has to be time dependent too, yes. So this is this dual interpretation that I just described. So now from the point of view of phase transitions, it's interesting because what you discovered that if you condition your ensemble on the trajectories of the system by fixing this time average current, you get a stationary ensemble which violates time translation invariance. Time translation invariance, which is spontaneously broken at this point.
Also space.
Eh?
Also in the space variable, no? You have a group.
Yes, but the space homogeneity is violated already when you have a boundary driven. Yes.
No, in your setup of the.
No, but I was thinking of yes, of course, also this translation in space. But what is the novelty is that phase transitions with spontaneous breakdown of time translation have never been seen before. Of course, you may ask whether there are conditions on these transport coefficients which tell you that in fact these dynamical phase transitions are not possible or they do not exist. And in fact, you can give conditions on these coefficients. I give you two examples. If this is, for example, this is satisfied by the simple exclusion. So, Bodino and Derrida, even if they didn't ask the question, were correct in what they were doing, because the simple exclusion, this is a stricter condition, but it is satisfied by the zero range process, for example. Okay. These are sufficient conditions. You may ask, well, okay, no, there are less. You may ask whether these conditions may be also necessary. In general, they are not. But more recently, 2 years ago actually, Spielberg and Ackermans in Israel have shown that under certain conditions, this condition become also necessary. And so they call it the analog, the non-equilibrium analog of the Le Chatelier principle, which is in thermodynamics is a principle of stability. Yeah, okay. So that also is an interesting thing. Suppose okay, suppose you have a system at these 2 dimensions, and you consider the current between 2 points, or between 2. Suppose you have something like this. So from a point here to a point here, and currents are very complicated in such a situation. But as far as fluctuation is concerned, everything goes as if you were on a one-dimensional system. And this phi is just the Lejeune transform of the functional phi j that I introduced before, and there is a purely geometric coefficient, which is the capacity of this capacity in the sense of electric capacity. I mean, which is a mathematical quantity, I mean, of this. So you see, there has been a lot of fallout of this approach, of follow-up, if you. Then there were this interesting, I mean, it's a hard paper to read. It's really a physicist-style paper. But it has a lot of content, because they calculate both microscopically using the beta ansatz on the simple exclusion. So it is a real tour de force. And then they calculate with using this macroscopic approach they discuss the possibility of these phase transitions, and they prove that, in the physicist sense that this exists. But then they find this beautiful, they find this beautiful expression for the moments of the charge of the integral of the current over a certain interval, so that using our usual formula, you see that it contains only the transport coefficients. So these are entirely universal. All the systems which have the same transport coefficients have the same moments. Another case which was interesting, and it's also a beautiful paper by these people, is that suppose it's called the single file diffusion. So you have in a one-dimensional system, you have a target particles, which can, and other particles cannot overcome this one. So you see, all the quantity of matter, for example, on the right, is conserved, because there cannot be. And this can be treated in great detail microscopically and macroscopically. And this is on the most beautiful example where this macroscopic theory and the microscopic theory gives exactly the same results in all possible situations. And what is interesting, you see, you are interested in the fluctuations of a single particle. However, you can express this in terms of fluctuations on macroscopic quantities. Why? Because you see, this integral of the density is conserved. The quantity of matter is conserved, which is on the right of this. And both doing microscopic calculations and macroscopic calculation, you get always exactly the same results. This is a beautiful subject, but I cannot. This is something rigorous. We published a long, unreadable paper on communication in the journal of the Current Institute, Journal of Pure and Applied Mathematics. And it's interesting because it's a problem that we solved in the infinite dimensional case where there is we didn't find any trace in the literature. Let me tell just qualitative what is. You see, take our non-equilibrium free energy. If you are in equilibrium, this essentially is a convex function. But if you are out of equilibrium, you may develop singularities. And this we proved for. So you have to take what is called the weakly asymmetric. The weakly asymmetric case with an external field, you use heavily the Hamiltonian structure, and you use heavily the structure of the unstable and stable manifolds of the stationary solution, and then and it's interesting because now you have you have a caustic in a functional space. So it's not simply in like in catastrophe theory in a five-dimensional case. And you see the typical profiles that for which you have this phase transition, you have a discontinuity in the derivative, and very similar to the Maxwell construction that you find when you consider. But I mean, this. I mean, it's a problem which is very difficult. It's difficult functional analysis to study this because you have this singularity in a functional space. So is the functional derivative which is discontinuous. And when this happens, it happens when you see you have two entirely different trajectories, which on which the work is minimal to reach the fluctuation. If there are two different trajectories, usually they are entirely different, then you have this phenomenon. Heuristically, but not in this context, so that I didn't speak of phase transition, but the non-differentiability at the physicist level of mathematics have been discussed by Graham, a German physicist, but long ago, I mean, in the 80s. So, now, in the last, let's say, 20-25 minutes, let me discuss an entirely different subject, but where the previous structure also enters. And that are thermodynamic transformations from a stationary state, general non-equilibrium, to another stationary state. I don't know if you are tired, I stop. But,
No, I think it's okay.
Go on.
Yeah, it's okay.
So, let's see. Suppose so you go in a time t, which in the end for quasi-static transformation will go to infinity. And you go from, for example, by changing the boundary conditions or by changing the external field, you go from a stationary state to another one. Okay, for example, you change the boundary temperatures or the boundary potentials, so on and so forth. And then what is the energy that you involved in this process? And then you have typically two terms. One is the work done by the external field, and the other one is the energy supplied by the reservoirs. Okay. Now you must realize that once we are out of equilibrium, if the system is out of equilibrium for an infinite time, you get an infinite work. Because to keep it out of equilibrium, you must spend a lot of energy. And of course, there are situations in which you don't care. For example, if your source of energy is the ocean or the atmosphere, so you have big sources of energy. But in order, if you want to discuss the energy balance, you must renormalize the work. And there is a very natural way to do it in this. Now this expression can be transformed, you see, by essentially transforming this surface integral into using the divergence theorem and so on, and using heavily, you see, and using heavily the Einstein relation, which connects locally the two transport coefficients to the equilibrium free energy. So it is not simply doing integration by parts. You do integration by parts to transform the surface integral into a volume integral, but you must use the Einstein relation. So it's use the physical information. And then you end up with this expression. You see that this is the variation of the equilibrium free energy, but calculated on the non-equilibrium profiles. For example, typically if you have a homogeneous equilibrium profile, the density is constant, for example, but once you put boundary condition, the stationary profile will be some curve. So you have to evaluate the equilibrium free energy in this. And then you have the dissipative part. So you see, this is our usual Holmes type dissipation, okay? And then you see, this is a positive term, it's a quadratic term. So if you throw it away, you have that the work you have to do is just larger than the variation in the free energy, which is one formulation of the second law, which is derived, as if you want, dynamically. But, so I don't. This dissipative part, you remember that our two currents are orthogonal. So, and you realize immediately that the term which gives you divergence is this part here. Because this is the current which survives when you keep the system out of equilibrium. It is the stationary current is this antisymmetric part. So there is a very natural way of normalizing it, which is throwing away this part. And then you have
Sorry, can you explain again what you mean by renormalizing it?
that you subtract this part here
Okay. But
from the dissipation.
why you want to remove it?
Because otherwise, when the time goes to infinity, you get infinity equal to infinity.
Okay.
So we renormalize by subtracting this part, and which is the current, the contribution of the current which exists in a stationary state. Now, the idea that the first people who realized that there was some problem out of equilibrium in terms were this Japanese owner and with a person called Paniconi, but who after disappeared, I don't know. And now Uno made some connection in finite dimensional case between large deviations and thermodynamics. But so there was this paper of 20 years ago, and this he called this energy that you need to keep the system out of equilibrium housekeeping energy, housekeeping heat. Actually consider very simplified situations, but anyway, it's interesting. And now this now what is interesting then is that at this point you get a strong you see the renormalized work, renormalized in this way, obeys the same clausus inequality as the total work for a finite time transformation. And and actually you have equality for quasi-static transformation, because for quasi-static transformation the symmetric part of the current is gives this integral is you see the current is infinitesimal, and so this is quadratic expression. Then you get an infinity which comes from this integration, but still goes to zero if you have exponential decay.
Yes,
So-
so the point is that Js goes to zero at infinity for...
Well, for when you do a quasi-static transformation, so you depart at each instant. It's like if time were frozen. And the current is infinitesimally small.
Yeah.
Because you go out of equilibrium only.
Yeah, I mean the integral in time of the current is finite. So the integral of the square of the current can go to
So
zero.
this integral, so this is, let's say, suppose this current is of the order 1 of this large time.
Yeah. Yes.
So this is 1 over this large time squared, but the integral gives you another time, so everything goes to 0 like 1 over t. And so you see, you get the clausus inequality for the normalized work, and which becomes equality for... So you see that actually the equilibrium free energy plays a big role also out of equilibrium when you consider thermodynamic transformations. Of course,
Yeah, but somehow behind this there is this picture that locally you are in equilibrium,
yes,
no? Because
yes,
you have
yes.
this small f which is the local.
yes,
Yeah.
yes. But otherwise you don't have hydrodynamics,
Yeah, sure.
because you must be able to define local variables. Okay. Now this I want to skip. Now, however, a real, and I think this would be the last Well, let's see. I will dedicate a few minutes to this. Any real transformation takes place in a finite time, a very large time with respect to the relaxation times of the system, but it's a very so we want to calculate the corrections to the ordinary, the first corrections of the hydrodynamical equations when the essentially we want to develop hydrodynamics in power, in inverse powers of a large time. Okay, so you rescale the time as you do when you do adiabatic transformation. Tau is a large time here, so you introduce a rescale time between 0 and 1. And then you expand both the solution of the density in terms of power of 1/2, the same for the current, and the same for the stationary current. You see reappearing in this expansion our V functional, so the non-equilibrium free energy. And okay, these are nasty calculations, but they are. But you see, so you get an infinite number of identities, but already the order 0 is very interesting because, luckily enough, you show that the infinities on both sides of the energy balance cancel, so you can have other identities. And you see, this is something that we didn't find anything in the literature. You have that the difference in the equilibrium free energy is related to the first correction of to hydrodynamics, and you see, you get this is the contribution of the external field, and this is G and R are the correction to the density, and G to the current. And then you have this term, because you see, you can go from one state to another one. For example, if you go from an equilibrium state to another one, you can go only, for example, by deciding to go only through equilibrium states. Then this terms is 0. But if you go also through non-equilibrium state, then this terms contributes. And this is a relationship that in principle can be verified experimentally. And actually you get an infinity of identities. I mean, as soon as you go on in the expansion become very complicated. But already this one requires some nasty calculations. Okay, now suppose you calculate the renormalized work to up to the second order in this. And then this coefficient B is a positive expression which contains the inverse of the correlation, two-point correlation functions. And you see, the diffusion has disappeared from this expression. This is natural because you are on a scale of time in which relaxations typically of diffusion disappear. So it's independent of the... But then, you see, you may try to optimize your transformation, your protocol, by minimizing this B. And this leads to a series of optimization problems. And I skip all the calculations because they're quite complicated. But the result is quite interesting. Because, for example, if you go through, you go from an equilibrium state, for example, you want to fill a container with a gas, and you go through homogeneous states, so you fill it slowly, and And then, I mean, you can calculate what is the optimum protocol for doing this, and so you can do the calculation explicitly, and you get a certain answer. What is interesting is the answer we got was identical with an answer doing with Langevin equation by Crookes. They are very well known now, this fluctuation relationship by Jarzynski, Crookes, and Galavotti-Cohen, and so on and so forth. And this result, which had been obtained also by them in a finite dimensional context. But then we want to profit, at least for an ideal gas, we are able to do the calculation. We want to profit from the fact that you have additional degrees of freedom because you have an external field that you can use. And then you may go through, contrary to any intuition, any physicist I have asked says, no, the best way is to go through homogeneous. And this is not true. You may go through non-homogeneous states, and this is much more convenient, and I will show why. So you made the calculation for an ideal gas, and you find that your answer is 2/3 of the final density, because the final equilibrium is homogeneous, while if you go through homogeneous equilibria, it's 1/8 this quantity. So you gain 75%. You gain a lot. And what is the transformation that does that? Is well, I will show you the picture. Instead of going slowly with this, you put all the gas you want to introduce near the walls of your container, and then you exploit the fact that this expanding can do some work for you. So this is a very general fact that if you have additional freedom, like having an external field, and the external field is the one which counteracts this expansion, and you do it slowly. So the principle is that you must have the system work for you. And if you have additional, now this type of problems are, I've seen in Lyon, there is a physicist who does in entirely different context optimization problems of this kind experimentally. And then the philosophy is very much the same. I give you only last information that if you do a thermodynamic transformation between one state and another, a stationary state and another one, and then you start, you can normalize your non-equilibrium free energy in such a way that the initial state is zero, and then the non-equilibrium free energy of the final state is nothing but relative entropy between the initial distribution and the final distribution. There's been some intuition of this I've seen in heuristic papers by people doing thermodynamics, and asking. But anyway, for the simple exclusion, I think you can prove it rigorously. This fact. So now, this theory is. So let's make some conclusion. Then I stop. So this macroscopic fluctuation theory allows another unified treatment of thermodynamics of non-equilibrium processes. And the interesting fact that this is a purely macroscopic theory, like, and of course, statistical mechanics provides models. And in various situations, you may have to solve quite difficult variational problems, but in some cases you can. And so you see, it has a role similar to the Boltzmann-Einstein theory of fluctuations, because it's the interface between the microscopic and the macroscopic. Because as a macroscopic theory provides thermodynamic functionals, but is related to the large fluctuations of the microscopic models. So large fluctuations come in at every step. So it's just the interface of this. Presumably, we think that they should have applications in biology, because that you have a variety of diffusive situations. Okay, now, usually this name, macroscopic fluctuation theory, is associated to our group in Rome, but many people have contributed to it. And especially we have been very much encouraged by Bernard Derrida. So now I cannot give you, I mean, there are very extensive, so the people are Lorenzo Bertini, Alberto De Sole, Davide Gabrielli, and Claudio Landin, that you may know is a probabilist. And we didn't have any formal instruction in physics, but he has learned by the same way as you learn a language. By discussing with us, he has learned something. So I always try to keep this group united in order that people were motivated. Even if the first three became mathematicians, they had been my students in physics, but then they degenerated. But still they understand physics. So here I pointed out only reviews. So we have, in 2006, here at the Newton Institute, I gave a course and Derrida gave his course. So this is the outcome, essentially the content of my course that we wrote all together. And then this is the Derrida course. And this is a very interesting review. Of course I recommend ours, but also Derrida is a beautiful review, and even, I don't know, until a couple of years ago, it was the most read paper in this journal. And it reads both his work and our work in a very effective way. And then we have an extensive review on the reviews on modern physics, but these questions of optimization problems that I discussed in the last part, these are only partially discussed here because they were completed after, and so I have added this paper, which appeared in the end of 2015, about this, how to fill a gas in a container. Now, for example, Albert Spohn objected that a real gas in which you have also momentum and so on may behave differently. I think actually it behaves even better, because if you include momentum, you have the pressure. I mean, the pressure is related to the momentum. So I think it will be even more true, the conclusion, which was here a diffusive gas. Okay. And I mean, we have been more or less in contact all the time with Derrida, Leibowitz, and then after some point with also Thierry Godinot. I would say that those are the people with whom we interacted more. And